So we've looked at how we can transform Taylor series by substituting in something like x squared for x or 2x for x, or we can subtract things from the series, or we can multiply something by the series, or multiply the series by something, I guess is the way to say that. You can also take derivatives of them. So for example, we have e to the x here. If we take the derivative of each piece, we get the derivative of 1 is 0, so I don't need to write anything there. The derivative of x is 1. The derivative of x squared plus 2 factorial will be 2x over 2 factorial. And then 3x squared over 3 factorial. And then 4x cubed over 4 factorial. And so on. Okay, well, if you notice, you can simplify all of those and get 1 plus 2 over 2 factorial is just 1, so it'll just be x. 3 over 3 factorial will leave 2 factorial on the bottom. Okay, if you're not sure how I got that, just consider that 3 factorial just means 1 times 2 times 3. So 1 times 2 times 3. So the 3's cancel, and then this is left, and 1 times 2 is the same as 2 factorial. Okay, same with this next one. We have 4 factorial. That's just 1 times 2 times 3 times 4. So the 4's cancel. And so I'm left with 1 times 2 times 3, which is 3 factorial. So if you look, that's exactly the same thing we started with. This is a perfect match for this up here. And that makes perfect sense because the derivative of e to the x is itself. So it makes sense that if you take the derivative of its Taylor series, you're also just going to get itself. Okay, here's another example. Sine of x. If you were to take the derivative of it, you would get 1 minus 3x squared over 3 factorial plus 5x to the 4th over 5 factorial minus 7x to the 6th over 7 factorial. And using the same method we were before of reducing those factorials, you'll get x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so on. And that should be familiar to you as one you've got memorized, and that is cosine x. Which again, we know the derivative of sine x is cosine x, so it makes sense that if we take the derivative of its Taylor series, we can get that. Now admittedly, we don't often do the derivatives because it's a lot easier in general to just do the derivatives of the normal function. But that is not always the case with integrals. Now this particular integral you see right here would not be very difficult to do just using normal integral rules. But actually the second example we'll see would be extremely difficult, in fact impossible to do with normal integral rules. So the reason this can be beneficial with integrals is that not every function can actually have an integral taken of it in a traditional way. In other words, u sub doesn't work, integration by parts won't work, none of those kind of strategies work. In fact, there are some integrals that are just plain impossible, as far as we know anyway. So the only way we can ever find the area under their curve is by doing something similar to Taylor series with them. Now, Taylor series is just going to offer us a approximation, because we're usually going to cut that series off at, say, 100 terms or 1,000 terms. But a calculator or a computer program can do 100 or 1,000 calculations pretty quickly, at least compared to a human. And so it's not really going to be that difficult to make that happen. So the Taylor series allows us to find integrals and area under curve where we might not be able to otherwise. So let's look at this example. You're going to start very similarly to what we were doing in the first video, where we start with what we know, which in this case is cosine x. And then we replace the x with x plus 1. So everywhere I see an x, I replace it with x plus 1. Okay, so now my integrand matches. Integrand is just what's inside the integral. And that's your first goal, is to make sure what's inside there matches. Now our next step is to go ahead and take the antiderivative. Sorry, my boundaries were very wrong there. Let's try that again. Okay, so I need to take the antiderivative. So antiderivative of 1 is x. Here I'm going to add 1 to the exponent and divide by that number. I'm going to again add 1 to the exponent and divide by that number. Add 1 to the exponent and divide by that number. And if you notice, we can simplify this and get x plus 1 to the third over 3 factorial, because 2 factorial is 1 times 2, so then times 3 would make it 3 factorial, and so on. This will become 5 factorial, and this one will become 7 factorial, and so on. Okay, now we do need to deal with the boundaries. However, in this particular case, well, if you plug in x for x, you just get the same thing back, and if you plug in -1, then everything is going to be 0 except for right here. So let's see, we would be subtracting that -1, so that would be adding 1. So you can fix that by just adding a 1 on the front end, and that will take care of it for you. Alright, now, this integral. This is one I mentioned that you can't take the integral of. There would be no way using traditional integral methods for us to take the integral of this particular function, at least not easily. Actually, now that I'm looking at it, there may be a way. No, actually I don't think there is. Okay, anyway, whether there is or not, there are some integrals out there that it's very difficult to take the integral of or impossible to, so this method is the only way they can really make it happen. Okay, so the first thing we want to do is try to get a function that matches what's inside the integral, what the integrand is. So we start with e to the x, because that seems to be the foundation or the building block. So we start with something like that. And then the next step is we need to substitute the x with -x squared. So everywhere I see an x, I replace it with -x squared. And I'm going to go ahead and simplify that. So it'll become 1 minus x squared plus x to the 4th over 2 factorial minus x to the 6th over 3 factorial, and so on. Notice when I have odd exponents such as 1 or 3, it keeps the negative. When I have even exponents such as 2, it becomes positive, just like normal with positives and negatives. So that's my first step. My second step would be to subtract the 1 over. So e to the -x squared minus 1 equals the same stuff, just the 1's been moved over to the other side. Tell you what, let's go ahead and add another term. You should be able to follow the pattern and know that next up would be this. Okay, now we need to divide by x. So I take everything and divide by x. So I just knock off a exponent, so it goes down 1. So -x plus x cubed over 2 factorial minus x to the 5th over 3 factorial plus x to the 7th over 4 factorial, and so on. So now we finally have a match. This matches what we originally had up in our integral, or integrand. So now we're ready to take the integral. So we do the integral from 0 to 1 of e to the -x squared minus 1 over x, and we simply take the antiderivative. Okay, we can't do this infinitely because we were going to have to actually plug in numbers. We can't just keep doing that forever and ever. So just for the sake of this problem, I'm going to limit us to 4 terms. Something we'll learn later is how you can actually figure out how accurate that is. It's related to the alternating series remainder theorem, if you remember that. So I'm just going to stop with the 4 terms I have here. So I'm not going to worry about the rest because I'm just going to be approximating using this method. So I take the antiderivative of these 4 pieces. That's going to give me -x squared over 2 plus x to the 4th over 4 times 2 factorial minus x to the 6th over 6 times 3 factorial plus x to the 8th over 8 times 4 factorial. And now I need to plug in 1 to all of those. So I got to plug in my boundaries. So negative 1/2 plus 1 over 4 times 2 factorial minus 1 over 6 times 3 factorial plus 1 over 8 times 4 factorial minus, well, if I plug in 0, this all just becomes 0, and so it's no big deal. So I just need to add the negative 1/2 and the rest of those terms together. Adding all those gives us negative 0.39576. We'll just round to that spot. And I'll just go ahead and tell you that you can determine that that is accurate to within something like 3 decimal places. In other words, it's no more than 1/1000th off by just looking at what the next term would be. So if you follow this pattern, you can see the next term would be negative 1 over 10 times 5 factorial, which gives you something like 0.000833, something close to that anyway. So your error for this answer is no bigger than this. So that proves you're accurate to within 1/1000th, which is pretty good. And you consider we just used 4 terms. So it would go pretty quickly. By doing 10 terms or even 20 terms, we would be accurate to lots of decimal places. So you can see how this really computationally wouldn't be very difficult for a calculator to get very accurate results.